All right, all credit goes to these people over here. Regular notation. And this is why we're going to say df equal gradient f dx dotted, I think. And then there's another thing I need to say. This is not the proper way, but this works. So we're going to say dx equal to, I believe it was er, and it's going to be h1 d something. So something like, how do I write this? Um, dr e data. Will this work? Er, and then d data. No, this won't work. All right, we'll call it d star for now. And then plus d, we'll just do this one for now. Plus, oh, yeah. Plus d z, well, we have to call it something else. Let's call it gamma for now. And then e z. Now we're going to say d data equals a change in the r direction, which is going to be like this, which is going to be basically dr, right? And this is going to be d data over here, which is going to be changed to d data. So this is going to be r d data. And d something like this is equal to dz. What this creates is the formula that dx I equals to dr er plus r d data e data plus d z e z. Some of these were obvious, which is the DZ one, and everyone else is actually not obvious. You have to figure that out by looking at the change everything, which is H1, H2, H3 that we discussed last time. So these changes over here are the reasons why this works. Over here, let me explain what I mean. These changes over here are the reason why it works, these three. And it was kind of evident, right, how I showed it off. If it doesn't make sense, here's another way to look at it. Again, we have a circular sphere. We have a radii. If we want to change in the r direction, is unitary. It just keeps on going. If you want to change it in the theta direction, what happens is that there's a change in r2, how you move it. So imagine you're like this over here. If you move if you move theta this way, you're changing r to move with it. Therefore, you're changing something else, the vector quantity. And then obviously z doesn't change anything except for nothing. So it's unitary again in z direction. So and z kind of changes r over, doesn't it? I have to think about that. I don't think so. I think it changed theta. No. Well, some of the coordinates goes like this, right? Some of the coordinates goes like this everywhere in reality, right? Like that, it makes a cylinder like this. So then you shoot the D like that. So no, it doesn't. I think everything checks out if I remember correctly then. It's a little confusing, but we get it, kind of. Anyway, then we have to write the F is equal to, I believe, FR. No. I believe it was something like A dr ER plus D. What was it called again? R d data E data plus C d z E z, which must equal to delta F, right? I think that's right. And another thing we have to write here is delta F is equal to FR dr plus F data d data plus FZ dz, and then EZ over here. Sorry about that. And we match it. So A equals to FR, B equals to 1 divided by R F data, and FZ equals C. So what that tells you is that the gradient F in polar form if is ER like this, FR, so it's like, okay. So with that said, now we can finally go into our Navier-Stokes. Why this was a little bit painful. You have to go with each and every vector. You know what? There's a reason for Google, and I think I just wasted everyone's time. Understatement of the century. But yeah, that's basically how you do it. You have to have, and this actually turns into dvr dt minus or plus, I don't remember, v data squared or something divided by r plus everything else, which is going to be equal to gradient. So it's going to be delta p over delta. I believe it's going to be the first one, so it's going to be r. Am I correct? Yes, I am, I think. And then the next section, if you do that whole process, which I'm not showing because I realized how painful that is. I did not know how painful that was until I tried to do it. So I take it back a lot of things, but in reality, this is what should get in the end if you want to try it all out. Um, do I have it in space? So honestly, search it up. Um, and then the last one, the energy one.